Hey, it's Mr. Shrum, and I am back again with a tutorial walkthrough. And today we're going to look at the universal wave equation. So after this lesson, you will use the universal wave equation to solve problems involving speed, frequency, and wavelength. So let's get into the introduction. Janice is enjoying her vacation in Hawaii. At one of the state's most beautiful beaches, she loves watching the waves hit the shore and go back into the ocean or recede. Ocean waves are periodic, meaning they repeat with a constant time period between waves. As the waves approach the shore, though, Janice notices that their wavelengths are shorter and that the waves slow down. She wonders why. In this lesson, you'll explore waves and their wavelength, speed, and frequency. You'll also see how to use the universal wave equation. So what is the wave equation? Before we look at how everything is related in a wave, let's review the meaning of each term. Wavelength is the distance between two consecutive crests or troughs from a wave, and it is typically measured in meters. So crest to crest, one wavelength, and has the same length as trough to trough. All right. So the top of the hill to the next top of the hill is one wavelength. Frequency is the number of wave cycles occurring per second. Its unit is the hertz, which is one cycle per second. And sometimes that's called second to the -1 power. But that's just a hertz. So if one wave passes in 1 second, the frequency is 1 hertz. If two waves pass in 1 second, that is 2 hertz. And lastly, period is the time in seconds it takes to complete one wave cycle. So the frequency and period of a wave are related reciprocally. And period equals 1 over frequency. And if you rearrange that, that means frequency is 1 over period. And that's what reciprocal means. It means one term is equal to 1 divided by the other term. So there's an activity called Wave on a String that you can use to simulate the relationship between frequency and wavelength. You can do that a bit right here. Make sure that's... So this is a PhET interactive simulation. First step is to click oscillate. We're gonna lower the damping to 0. And let me hide this meeting control. So we click the oscillate option, drag the damping slider to 0, select the no end option. Keep tension set to high. So tension's already at high. We're gonna click no end up here in the upper right-hand corner. And so we're just gonna look at that wave go. Check the rulers box and then drag the frequency slider to the left and right to change the frequency and see what happens. Okay. So we'll click the rulers so we can measure stuff. And I'll use slow motion. Just easier to see what's actually happening. And so the frequency is at 1.5 hertz. So let's go to 1. There we go. So like we said, it looks like that slows down the wave. Now, I sped up the frequency, not sped up the frequency, I increased the frequency. And so you have more waves per second. But the waves are bigger with lower frequency. You see that? Or they're longer waves. Anyway, part A, you're supposed to put the frequency at different hertz and then measure the wavelength. And these should be about what you get. So what's the relationship between the frequency and the wavelength? The higher the frequency of the wave, shorter the wavelength, and then longer the wavelength, lower the frequency, okay? Frequency and wavelength are inversely proportional. As a test, I applied frequency and wavelength. All the values fall in the range of 1450 to 1725. Since my length measurement could be plus or minus a centimeter or two, it seems like a pretty good agreement as a sample answer. Higher frequency, shorter wavelength, lower frequency, longer wavelength. Wave speed is constant in deep water, but as waves approach the shore where the water is shallower, the speed decreases and the wavelength becomes shorter. That's because the water's depth is less than the length of the wave. When the water is much shallower than the wavelength, the bottom part of the wave slows more than the top part. The result is that the wave stops being a smooth curve and the top curls over the bottom. As the speed of the wave decreases, the wavelength also decreases. In other words, the wavelength and the speed of a given wave are directly proportional to each other. The opposite is true of the relationship between frequency and wavelength. In the simulation, as you increase the frequency of the wavelength decreased. As you decrease the frequency, the wavelength increased. So the frequency and wavelength of a wave are inversely proportional to each other. Now let's see how frequency and wavelength are related to a wave's speed or velocity. We know that speed, v, or the velocity of a moving object is the distance covered by the object per unit time, t, d over t. In the context of waves, the distance between two crests is the wavelength. T is the time it takes to complete one wave cycle, which is a period, t. So we can rewrite the speed formula by replacing distance with wavelength and time with period. So v equals wavelength divided by period. And since period, t, is the inverse of frequency, f, we get speed is equal to wavelength divided by 1 over f. And if you rewrite that, that means the speed of a wave is equal to wavelength times the frequency of the wave. This is the universal wave equation. Speed equals wavelength times frequency. So here's an example of using the wave equation to solve for the velocity of a wave. A sound wave from a musical note has a frequency of 440 hertz. At 30 degrees Celsius, its wavelength is 0.79 meters. What's the speed at that temperature? We're going to use this universal wave equation Speed equals wavelength times frequency. The wavelength is 0.79 meters. The frequency is 440 hertz. Substitute the value for these variables in the universal wave equation to get 0.79 times 440, 347.6 meters per second. Here's another example. You're given the frequency, the speed. Now you're solving for the wavelength. So you rearrange the equation to solve for wavelength. Wavelength equals speed divided by frequency. And then you just plug in the numbers. No problem. Now there's also problems where you need to solve for f, the frequency. So calculate the frequency of a sound wave traveling at a speed of 340 meters per second in air, given that the wavelength is 0.66 meters. So we can rearrange the equation. F equals the speed of the wave divided by the wavelength. So F is equal to 340 hertz divided by 0.66. That equals 515 hertz. And I will stop the lecture there for now, and we'll pick this up next time. But until then, have a good one, and I will see you guys soon.